Welcome to the deep dive. We're jumping straight into one of those really core choices you face as a programmer, starting something complex. It's this constant battle, right, between like technical perfection and just getting things done smoothly.
Absolutely. That's the heart of it. Do you go all out, pick the absolute best, most hyper-optimized tech for every little piece? That's polyglotism.
Or do you stick with what you know, well, maybe one main language or stack, even if it's not perfect everywhere, just to keep things manageable?
Exactly. And today we're diving into a fascinating case study of that first approach, technical idealism, you could say. It's a key value store called Polystore.
Right. And the interesting thing here is they use three completely different languages: Rust, Go, and Python, all working together.
Yeah, chasing optimization. So our mission today is, well, first, to unpack the why. The technical thinking behind using Rust here, Go there, Python over there, it's clever stuff.
But then there's the twist.
Then we flip it. We expose the hidden costs, the operational headaches, what we're calling the polyglot paradox. How optimizing each little piece can actually create massive complexity for the whole system.
Okay, let's get into it. Polystore v1.0. Why three languages? I mean, that just jumps out as complex from the start. What problems were they really trying to solve with that specific mix?
Well, the core idea is, as you said, right tool for the job. The needs of a storage engine, an API coordinator, and a client interface are just fundamentally different. They have completely different goals.
Okay, let's break that down. Start at the bottom, the storage engine. That's where the data lives. Speed and reliability are king. And that's Rust.
Right. Rust is there primarily for two big reasons: predictable performance and memory safety. Performance-wise, it competes with giants like C++-wise, but critically, it avoids garbage collection pauses.
The stop the world problem.
Exactly. Languages like Java or Go, they sometimes need to pause everything briefly to clean up memory. Rust's ownership system manages memory constantly without those pauses, so you get really low predictable latency, which is vital for a storage engine.
Predictable is key there. And the safety. That's Rust's big selling point, isn't it? The ownership model.
It's huge. The compiler itself acts like a super strict code reviewer for memory issues. It checks your code before it even builds using the ownership and borrowing rule.
So it catches bugs before they happen.
It prevents whole categories of really nasty bugs. Things like dangling pointers, where you try to access memory that's already been freed, or data races, where multiple threads mess with the same data unsafely. Getting that guarantee at compile time for a complex concurrent system like a storage engine, that's a massive win for reliability.
Okay, so Rust for the core storage. Fast, predictable, safe. But that data needs to get in and out, handle potentially thousands of users hitting it at once. That's the API server layer, and that's Go. Why Go?
Go shines for I/O-bound tasks, like managing tons of network connections simultaneously. Its killer feature here is Goroutines.
Right, Go's lightweight concurrency.
Exactly. They're not like traditional operating system threads, which can be heavy. Goroutines are managed by the Go runtime itself and are incredibly lightweight.
How lightweight are we talking?
Often just a few kilobytes of memory to start. This means Go can easily handle thousands, even tens of thousands of concurrent connections, sort of a one goroutine per connection model without overwhelming the system.
And that avoids bottlenecks you might see elsewhere.
Yeah, it gets around limitations like Python's GIL, the global interpreter lock, which restricts true parallelism for CPU-bound tasks, or Node.js's single-threaded event loop, which, while efficient, can be blocked by long-running operations. Go is built for this kind of network concurrency.
Okay, Rust for storage, Go for the API traffic cop.
Yeah.
Then there's the third piece. Python, just for the client library people use to talk to the API. Why not just say, Go for the client too? Keep it to two languages.
That's a really good question, and it points to a different priority for the client. It's all about developer ergonomics and speed of development.
Making it easy for people to use.
Precisely. Python has such a massive, mature ecosystem. Libraries like requests make interacting with APIs incredibly simple. You can write a client script really quickly. While you could use Go, Python lowers the barrier to entry for users. Here, ease of use trumps raw performance.
Okay, I see the logic. Each language is arguably the best fit for its specific job, technically speaking. But this is where the polyglot paradox comes in, right? The hidden costs, the analysis flags.
Exactly. This is the trap. You optimize each part locally, but you create complexity globally. The technical wins come at a significant organizational and operational price.
What kind of price? We're talking more than just, like, technical debt.
Oh yeah, much more. You now have a distributed system, fundamentally, just in terms of its build and deployment. 3 different runtimes: 3 different package managers, Cargo for Rust, Go modules, pip or poetry for Python,
Great.
3 build pipelines.
Wow. Just maintaining that sounds like a job in itself.
It is. And think about debugging. A single request might flow through Python, then Go, then Rust. Trying to trace an error across those boundaries, you need really sophisticated logging, tracing, observability tools just to figure out what's happening. It's a huge step up in complexity.
And then there's the people problem. The analysis mentioned governance and overhead.
Yeah, think about integrating common tools like a message queue or a monitoring agent. You need libraries, SDKs for each language. Someone has to find them, learn them, maintain them. It slows everything down.
And the bus factor. That sounds ominous.
It's a critical point. It basically asks, how many key people could leave or get sick before the project grinds to a halt?
Because the knowledge is split across languages.
Exactly. Your Go expert probably can't easily jump in and fix a complex memory issue in the Rust storage engine. Your Rust guru might struggle with Go's concurrency patterns. You create these knowledge silos.
Which makes hiring harder too, I bet.
Yeah.
You need specialists in all three.
Much harder and more expensive. Unless you're a huge company like Google, finding and retaining deep expertise in multiple distinct ecosystems is a real challenge. The risk goes way up.
Okay, so deep cost there. Now let's talk about how these different parts actually talk to each other. Polystore uses 2 different methods, gRPC inside the system and REST for the outside world. Why not just pick one? Maybe the faster one, gRPC.
Well, again, it's about different needs. The communication between the Go API server and the REST storage engine needs to be incredibly fast and reliable. The communication between the outside world and the API server needs to be accessible and easy to use.
So different protocols for different jobs. Let's look inside first. Go talking to Rust via gRPC. Why is gRPC the choice for that internal high-speed link?
Performance, primarily. Benchmarks consistently show gRPC outperforming REST JSON, especially for this kind of service-to-service communication. We're talking potentially 2.5 times the throughput, maybe 2 to 3 times lower latency on average.
What makes it so much faster?
A couple things. First, it uses protocol buffers, protobuf, for encoding messages.
Instead of JSON.
Right. Protobuf is a binary format. It's much more compact than text-based JSON messages can be, like 50% smaller or even less. That saves bandwidth and makes parsing way faster.
Binary is just more efficient for machines to handle.
Exactly. Plus, gRPC is built on HTTP2, which supports things like multiplexing, sending multiple requests and responses over a single connection without them blocking each other. It avoids head-of-line blocking.
Okay, so faster, more efficient. Any other benefits internally? Safety.
Yes, a big one. gRPC uses a schema-first approach. You define the structure of your messages and services in a .proto file.
Like a contract.
Precisely. This contract is used to generate code for both the client, Go, and the server, Rust. It enforces type safety at compile time. If you change the API in a way that breaks the contract, it just won't build. That eliminates a whole class of integration errors you might only discover at runtime with the REST JSON.
So gRPC internally for speed and safety makes sense. But then for the Python client talking to the Go API, they stick with plain old REST JSON. Why accept the performance hit there?
Because accessibility and developer experience trump raw speed for the external interface. REST is, it's the lingua franca of the web, right?
Everyone knows it. The tooling is everywhere.
Exactly. You can use curl, Postman, your web browser, any standard HTTP library in any language. JSON is human readable, which helps a lot with debugging and just understanding what's going on.
Whereas gRPC requires setup.
Yeah. Using gRPC externally would mean forcing your users to find the .proto file, install gRPC tools, generate client code. It's a significant barrier to entry. For external users, simplicity and ease of integration are paramount. REST-JSON delivers that. Optimize for machines internally, optimize for humans externally.
That dual protocol approach seems like a smart trade-off, actually. Okay, let's dig deeper into the storage engine itself, the Rust part. The analysis mentions it uses an LSM tree, a log-structured merge tree. This design is known for being great at writes, but what are the trade-offs? What challenges does this choice introduce that maybe aren't obvious at first glance?
Right. The LSM tree is fantastic for write throughput because it basically turns random writes into sequential writes, which disks love. It buffers writes in memory, the men table, and then flushes them to disk in sorted batches, SS stables.
Sounds efficient. What's the catch?
The catch is what engineers call amplification. There are several kinds, and they represent the hidden operational costs of that write speed. This is often what separates a toy project from a production-ready database.
Okay, let's break down amplification. First one, Write amplification.
Rate amplification means that for every byte of data you logically write into the database, the system might end up writing many bytes physically to the disk over time.
How does that happen?
It happens during a process called compaction. As new data gets flushed, the LSN-free structure grows across multiple levels on disk. To keep reads efficient and clean up old data, the database constantly runs background tasks that read existing data files, merge them, write out a new combined file, and then delete the old ones.
So data gets rewritten multiple times.
Many times. This constant rewriting consumes a lot of disk I/O bandwidth, and critically, it wears out SSDs much faster. SSDs have a finite number of writes they can endure, so high write amplification directly impacts hardware lifespan and operational costs.
Ouch. Okay, so writing is fast initially, but costly long-term for the hardware. What about reading data back out?
That's where read amplification comes in. Because updates and deletes are just new records being written, finding the current value for a specific key isn't always straightforward.
You might have to look in multiple places.
Exactly. A single GET request might have to check the in-memory memtable first, then potentially multiple SS-stable files on disk, starting from the newest and going back until it finds the key or confirms it doesn't exist. Each file check could mean a disk read.
So one logical read becomes multiple physical reads.
Potentially, yes.
Yeah.
This leads to higher read latency, and crucially, it can be unpredictable latency, especially under load or for keys that haven't been accessed recently. And reads for keys that don't exist can be particularly slow because you have to check everywhere.
Right. You have to exhaust all possibilities. And there's a third amplification.
Space amplification. Because old regions of data and deletion markers, often called tombstones, aren't immediately removed, they stick around on disk until a compaction process cleans them up.
So the database takes up more disk space than the actual live data requires.
Significantly more, potentially. You're paying for storage that's holding data that's technically obsolete but hasn't been garbage collected yet by compaction. This impacts storage costs and backup sizes.
Wow. Okay, so the LSM tree gives you blazing writes, but you pay for it with write, read, and space amplification, serious operational concerns. So wrapping this up, Polystore v1.2 sounds like a brilliant technical demonstration, a great learning exercise, but the analysis points out huge gaps for production. Things like replication, security, scaling, handling failures, these were all basically ignored.
They were out of scope for v1.0.
So what's the big strategic takeaway? How do you move from this v1.0 sandbox, maybe running in Docker Compose on one machine, to a real robust v2.0 that can handle production load and failures?
The core strategic shift is acknowledging and paying the distributed systems tax. You have to move beyond optimizing the code on a single machine and start designing for scale, resilience, and operability.
And what does that look like in practice?
Well, you're likely moving to something like Kubernetes for orchestration, managing deployments, scaling automatically, handling node failures. You absolutely need data replication and partitioning or sharding so the system isn't limited by one machine's capacity and can survive machine loss.
And consistency becomes critical across those replicas.
Absolutely. You need a consensus algorithm like Raft or Paxos to make sure all the copies of the data agree on the state, especially during failures. This guarantees data integrity. v1.0 likely had none of that.
And security. v1.0 seems to have ignored it completely.
Can't do that in v2.0. You need a proper security model, probably zero trust, that internal gRPC connection between Go and Rust. It needs mutual TLS, MTLS, so the services authenticate each other. You need authentication, authorization, encryption, the works.
So given all these operational realities, the distributed systems tax, the organizational friction of polyglotism we discussed earlier, the talent silos, the tooling overhead, does the analysis suggest sticking with 3 languages for v2.0?
The pragmatic conclusion is probably not. While v1 users' polyglot approach was technically interesting, the operational and organizational overhead is likely too high for most teams building v2.0.
So what's the likely recommendation?
Standardize. Consolidate the server-side components, the API and storage, into a single high-performance language, probably Go or Rust. Maybe keep Python for the client if developer ergonomics are still paramount there. But reducing the number of server-side runtimes dramatically simplifies building, deploying, monitoring, and staffing.
You trade that last bit of theoretical, localized performance for massive gains in global simplicity and maintainability.
Exactly. The v2.0 goal isn't just run fast code, it's run reliably at scale, survive failures, be secure, and allow the team to actually manage and evolve the system over years. That often points towards simplification, even if it means giving up on the perfect tool for every single microcomponent.
It really underscores that architecture isn't just about tech choices. It's deeply intertwined with team structure, operational capacity, and long-term costs.
Absolutely. It's a socio-technical system.
Okay, so here's something for you, the listener, to think about. If you were tasked with building Polystore v2.0 right now, knowing everything we've just discussed, the allure of Rust's safety, Go's concurrency, Python's ease, but also the heavy tax of polyglotism and the demands of distributed systems, would you keep all three languages to squeeze out every last drop of performance? Or would you consolidate, maybe down to one or two, prioritizing team velocity, operational simplicity, and long-term maintainability? What's the right trade-off for you? Mull that over.